So let us start this today. You have the circuit and truth table of NOR gate. In this circuit and truth table, you find that the two transistors, transistor TA and transistor TB, two well matched, we can say well matched transistors. What do you mean by well matched? The well matched transistor is the transistor which beta will same. Beta is HFE. HFE. That is common emitter current gain. HFE. So these two transistors have the same HFE, that is well matched, are connected, parallel connected. So the collector of the terminals of the transistor are connected at one point. That point is said to be P, and the emitter of the terminals are connected at point E, and which is grounded at this moment. And these two bases of these two transistors act as input A and here input 2. 1 and 2 are the two inputs named as A and B. So these two inputs are here and they are connected with the power supply VCC with RA. Now in the circuit of NOR gate, two or more transistors are connected in parallel, and there are basically 4 steps. 4 steps. Why it is 4 steps? Because these are the 4 possibility of the table, and these steps are, say, step 1. First is step 1. What we want to step 1? Step 1 corresponds to the first row. What is the first row? When the VA, this voltage at this point is say VA, at this point the voltage is VB. VA is equal to VB is equal to 0. So these two columns A and B has the value 0, 0. So the input of transistor A, one is 0 and transistor B is 0. And when these two values are 0, so these inputs are 0, IB is 0. This indicates that IB is 0. And if IB is 0, so transistor A and transistor B both are in cutoff region. Both are in cutoff region. What do you mean by cutoff region? You see, these are the characteristics curve corresponding. This IB is equal to 0, and here IB is not equal to 0. This IB is not equal to 0, and this part is cutoff. So if it is cutoff region, so this cutoff region, that is TA and TB, exist at the same time here. And this part is the saturation. This part is saturation, and here this is the DC load line, and this load line have the point Q, operating point. So at this point, step 1, VA is equal to VB is equal to 0. So IB is equal to 0, and transistor A and transistor B both are in cutoff region. So what KVL said? This KVL, Kirchhoff voltage law, if you apply this Kirchhoff voltage law, that is V output is equal to VCC minus IC RC. What IC? IC is equal to beta into IB, and IB is equal to 0. So this beta into 0, and therefore IC is equal to 0. So if IC is equal to 0, this value is equal to 0. So V0 is equal to VCC. VCC means 5 volt. 5 volt means high. So the output is high, and this is the high. So step first, that is both transistor in cutoff. So in both in this case, that is when transistor is cut off, the output, this output will be 5 volt. This output is 5 volt. It means these two transistors, transistor A and transistor B, both are not working. So what happens? The complete power that is given, VCC, is on the output part, and that's why it is high. And in all other cases, you see the output is low. Now we have to see why this going to be happen. So we will take the step 2. Say step 2, in this step 2, when TA, transistor A, is not equal to 0 and TB is equal to 0. So what happens? You see in this characteristic curve, that is this IB is equal to 0, and here it is this IB is not equal to 0. This is not equal to 0. So this TB is here in cutoff region, and since this is not equal to 0, so this is the place of TA. TA will be switch over to the saturation region, this region. So what happened? In TA is not equal to this VA, so IB base current across the transistor A, that is VA upon RB, which is not equal to 0. So the corresponding collector current, that is IC is equal to beta into IB, and this is again not equal to 0. So what KBL said? KBL said that V output is equal to VCC minus IC RC. So this VCC minus beta, VCC is beta VA upon RB into RC. So what happens? In this way, the current is flowing. And then there is a potential drop, VCC minus this value, and then this will, due to the flow of the current, there is a potential drop, and therefore V output is approximately 0. And if it is 0, so it will be the low. So the case 2, that is either of the transistor is in saturation region, the output will be low. And similarly, we take the step 2, 3. Step 3 is when this transistor, when VA is 0 and VB is not equal to 0. This VB is not equal to 0. So what happens? In this case, again, in the same way, this is the IB is 0, and here it is the IB is not equal to 0. So at this time, this is the cutoff, and this is the cutoff. So the transistor, this transistor TA is here, and the transistor TB is shifted to saturation region. This is the IC region. This is the IC saturation region. So in this case, the IB base current across the transistor B is equal to VB upon RB, which is not equal to 0. And this implies IC is equal to beta into IB, which is again not equal to 0. So again, the KVL is equal to V0 is equal to VCC minus IC RC. So at this time, current is flowing through transistor A, and this is VCC minus beta, and this value is VB upon RB into RC. So due to this potential drop across the RC, this the output will be 0, which is low, that is V0. And the final step, that is step 4. Step 4 said that when both inputs are finite, that is VA is not equal to 0, VB is not equal to 0. Both are finite. So what happens? This IA, IB across the transistor A is VA upon RB. This is not equal to 0. And IB at B, from B transistor, VB upon RB, this is again not equal to 0. Both are finite. So what will be the case? The IC will be sum of these two currents. Sum of these two currents across the base. So this IC is some finite value which is not equal to 0. And then the KVL, again KVL states that V output is equal to VCC minus IC RC. VCC minus IC RC, which is equal to 0. And this is again low state. And if we see in case of this diagram, this characteristic, we find that both the transistor, this is the IB is equal to 0. Here it is IB is equal to 0. This IB is not equal to 0. So this transistor TA and TB, both the transistor are in saturation region. And here it is cutoff region. So no transistor in cutoff region at this time. So what we find ki NOR gate is opposite to the OR. In OR gate, either of them is finite, then output is finite. Here it is, if both are 0, then output will be finite. So these are the circuit discussion regarding the RTL-NOR gate. So in this case, as it is very clear that the input case for the input voltage say VIA and VIB, the variation of the output voltage V0 can be visualized as. So if you see, this is the VI, anyone say VIB and VIA. Suppose this is equal to 0, and there is a corresponding V0. So the variation is, this is the constant, and then there is a change, and here it is this one. So from this point, this value is here. So up to this point, this value is 0.65 volt, and this value is 0.8 volt. So from this point to this point in the input voltage, there is a change. There is a change in the case, and this value, this output, this V0, this VCE, and this VCE is saturate, and it is 0.2 volt. This is 0.2 volt. So in this case, we can define as the saturation current, collector current saturation collector current IC sat is VRC upon RC, and that is VCC minus VCE. VCE sat divided by RC. So whatever the value that we are having in this case, that is, we can say, take the typical value for the typical values. Typical values means numericals. Typical values means we are taking numericals. The numericals for this case of discussion is, say, VCC is 3 volt and RC is 640 ohm. 640 ohm. Then we can find IC saturate is equal to 3 minus 0.2 volt divided by 640 ohm. So this value is 4.3 milliampere. This value is 4.3 milliampere. The saturation parameter, this saturation parameter is one of the important. Saturation parameter is sigma, is defined as sigma is equal to IC upon HFE into IB. HFE into IB. And in saturation region, in the saturation region, this IB is greater than IC upon HFE. IB is greater than HFE, and we can take this value. Suppose this value is IB. IB is equal to IC, 4.3 into 10 to the power minus 3 ampere. And this saturation parameter is 0.85. And this is beta is 50. So this IB is equal to 0.1 milliampere, that is 100 microampere. So this is the IB, and the characteristic for the saturation, that is saturation parameter here, and this is the voltage. So we find this is something like this. So this value corresponds to 0.85, and this value is correspond to the saturation voltage. Voltage is VCE. It is 0.2 volt. Is 0.2 volt, and here this value is 1. Saturation parameter is 1. So the base voltage in this case is VB, and this is VBE plus RB into IB. RB into IB. This base emitter voltage is 0.75 volt for silica, and others, this is RB is 540, and this is 0.1 into 10 to the power minus 3 ampere. So this value is 0.75 volt, and here is 0.045. So this value is 0.8 volt. That is BB, base voltage. So this voltage is required for saturation of the transistor. And this saturation of the transistor, this value is very important in the case of the discussion of the other logic circuits. Other logic circuit, we like to discuss about the next important circuit is very important. It is DTL. DTL is very simple, diode transistor logic. Diode transistor logic. So in case of the diode transistor logic, let us draw a circuit, and we circuit for this is a VCC here, and this is the RC, which is 2 kilo ohm resistance, and then this resistance is say R. Again, this is 2 kilo ohm resistance, and this point is a P point, and this point is connected to the diodes. These are two diodes, and here it is transistor. Here it is the another transistor. This transistor, there is a resistance. This resistance is RB, and this is minus VBB is equal to minus 2 volt. Here it is emitter. This is collector, base. This diode is D1 and this diode is D2. And the input diodes are given as this is A point, B point, and C point. This diode is DA, this diode is DB, and this diode is DC. And this point is finally VO. Now the DTL truth table regarding NAND gate. Truth table regarding NAND gate. This is A, B, C, A, B, C, and V output. This is V output. So suppose this is 0, 0, 0. The value is 1. This value 1, 0, 0 is 1. This value is 0, 1, 0. This is 1. This value is 0, 0, 1. This is 1. This is 1, 1, 0. This is 1. This is 1, 0, 1. This is 1. This is 0, 1, 1. This is 1. And this is 1, 1, 1. So this value is 0. This value is 0. So in this way, we have two cases. Say case 1. In case 1, when at least one input at diode DA, DB, DC is at 0 voltage. So what happened? suppose this is a diode, say the diode DA. This diode can be expressed like this. There is a N, here it is P, and these are the charge carriers electrons, and here it is the charge carriers are hole. And this is the correct connected. Somehow it is a VCC. This point, if VA is 0, what happened? If VA is 0, so in this case, the charge carrier, and this is positive, so the junction is forward bias, this 0 and this is positive. So electron experience attractive force towards the junction, and due to that the electrons cross the junction. This electron cross the junction. So due to forward bias, the current is flowing. Current flow across the junction. So what will be the potential? This potential is at this point, when we say it is 0, virtually it is not equal to 0, it is say 0.2 volt. And when the current is flowing, then at this junction, the voltage is 0.75. The voltage is 0.75. So the total voltage is 0.95. This is 0.95. So what happens in this way, if the current is flowing, so at this point is VP, and the VP is 0.95 volt, 0.94 volt. So at this point, the voltage is 0.95 volt, and we required the required voltage for conducting the diodes. Which diodes? D1, D2, and diode corresponding VE in the transistor. So this is nothing but, you can say this is 3 into 10 to the 3 into 0.65. So if it is there, then this much amount, voltage is required. This much amount is voltage required for conducting. But the voltage at P point is 0.95 volt, which is less than the voltage required, what is 1.95 volt, or sometime it is 2 volt. Therefore, the transistor is in cutoff region. Transistor is cutoff region. So what happens? KVL says this V output is equal to VCC minus IC RC, and if it is cut off, so the IC is equal to 0 because IB is equal to 0. So this value is VCC, that is plus 5 volt, and it is high. So any one of them is 0, then this case will be high. So output will be high. This output is high. So this is, output is high. Now case 2. What case 2 is? All of them. Case 2 is for the potential drop at point P is as the ID is current ID, the current ID is equal to VCC minus VP upon R. So what is, how much VCC? We see this VCC, that is 5 volt minus VP. In this case, if you can consider the all of them is a 0.75, so 3 into 0.75, 75 volt divided by, this is 2 kilo ohm resistance. So this value is 2.75 volt upon 2 kilo ohm. So this is 1.4 milliampere. This is ID. And this ID generates the current IB. IB is equal to this ID minus IRB. IRB. How much IRB? This is IRB is 0.75 minus of minus 2 upon 20 kilo ohm. So this is 0.14 milliampere. This is the just, this is minus VBB to the transistor, this case. So this current is IRB and here it is ID. So this is IB. So IB is equal to this much, that is 1.4 milliampere minus 0.14 milliampere, and this is 1.26 milliampere. And this value gives the finite IC, which is not 0. So transistor is, that is transistor is in saturation region. Saturation region. So what KVL said? KVL said the V0 is equal to VCC minus ICRC, that is finite value. So it is 0. So it is low state. Low state. So in the first, all the cases, if any one of 3 inputs is 0, then output will be high. And if all the inputs are high, then the output will be 0 because the transistor in saturation region. So in one case, that is all the inputs are high, there is the potential develop across the VP, which will sufficient to conduct, the diode D1, D2 and transistor. So it is the conducting state. Here transistor is conducting state. Transistor is conducting state. And in this case, transistor is non-conducting state. Non-conducting state. So this is the working of the simple working of DTL. So this is about the DTL part that we have to discuss. So now it is a time to